So in this video, as a part of basic electrical engineering course, we are going to discuss about series connection and parallel combination of resistance. So and then after we will look at voltage division rule and current division rule. So let us begin with series combination of resistance and parallel combination of resistance. So a resistance are said to be connected in a series if the same amount of current flow through the resistor. So say for example, if we take a case where two resistors are connected in series and it is connected with a voltage source, so R1 and another is R2, and those two resistors, let's say, connected in series. Now V in is a voltage source and first resistor is R1 and R2. Now when we applied a V in, so this voltage get divided among two resistors. Say for example, if V1 is divided a drop which is there across R1 and V2 is drop across R2. So in the overall sense we can write that this voltage which is V input is the summation of V1 plus V2. So here we can write from the Ohm's law. Ohm's law states that the potential drop across any resistor will be the multiplication of current which flows through the resistor into a resistance value. So if we connect R1 and R2 in series, and if we connect a voltage source V in, so let's say I current flows through the series combination. So the current I enters from R1, leaves at the other end of R1, and then again enter from the front end of R1 and leaves at the last end of R2, and in this way it is flowing through the circuit. So here the V1 can be found by I into R1. In the similar way, V2 can be found I into R2. Now here we have to find the equivalent resistor. So if we replace R1 and R2 with an equivalent resistor, so what we expect that the amount of current which is flowing through this combination should remain unchanged. So let's say if I replace this R1 plus R2 combination with one equivalent resistor, so the circuitry will look like this. So this is my R equivalent, and we expect the same amount of current which is I, which flows through the R equivalent. Now here the total voltage V will appear across R equivalent. Therefore we can write as per Ohm's law that, let's say, and this is my V in, right? So V in equal to R equivalent into I current, right? So from equation number, let's say 1 and 2, we can write R equivalent. So we can compare both the equations. So we can write like I into R equivalent will be equal to I into R1 plus I into R2. So if you take I as a common, so in the overall sense we can write like R equivalent equal to R1 plus R2. Okay. So now let's say if you connect n number of resistor, let's say R1 to Rn in the series connection, then equivalent resistor can be found like R equivalent is summation of R1 to Rn. So this is all about series combination of resistor. Okay. So now let's move to a parallel combination of resistor. Okay. So this is the final formula for the series combination. Now let's discuss the parallel combination of resistor. So in parallel combination, what is the mandatory condition? So if two or more than two resistors are said to be connected in parallel, if a voltage which appear across those resistors will be same. Say for an example, if I have one voltage source V in, and if two resistors are connected as shown here. So those two resistors can be only said to be connected in parallel if voltage V in is the supply voltage, and here this appears across this R1 resistor as well as this R2 resistor. Now the amount of current which flows, so main current is, let's say, I. So this current get divided into two parts, one is I1 and another is I2. So from that we can write here I equal to I1 plus I2. Now this V in appears across this R1 resistor. So from the Ohm's law we can write like I1 can be given by V upon R1. In the similar way we can write for I2 also. So I2 can be given by V upon R2. So when we substitute here in this equation, we can write a final equation which is I equal to V upon R1 plus V upon R2. Now if we replace this R1 R2 combination with equivalent resistor, so we can write let's say if we replace with one equivalent resistor R equivalent, so we expect same amount of current which is I, and here it is equivalent resistor, only one resistor, right, equivalent, and V in. Now with that what we can expect the value of current, so I can be given by V in upon R equivalent. So see, we can compare this equation number, let's say 3 and 4, and from that we can write here that V upon R equivalent will be equal to V upon R1 plus V upon R2. So if we take V as a common, so we can write here that V upon R equivalent is nothing but 1 upon R1 plus 1 upon R2. So this is the equation for parallel combination of resistors. Now let's say if you have connected n resistors in a parallel, so you can write 1 upon R equivalent will be nothing but 1 upon R1 plus 1 upon R2 plus 1 upon R3 up to 1 upon Rn. Okay, so this is the final formula to find the equivalent resistor when they are connected in parallel. Now let's move to the voltage division rule and current division rule. So let us first of all start with voltage division rule. So voltage division rule used in the circuit analysis. So let's say, and it is applicable when two or more than two resistors or any elements are connected in series connection. So let's say if we have two resistors here which are connected in a series connection. and the source voltage is V in, and this resistor R1 and R2. Now we have already derived the equivalent resistor of series combination, so the current which flows through this R1 R2 when they are in series, so this can be easily found like V in upon series, they are in series, so R1 plus R2 is equal to my overall current I. Okay, now let's say see, ultimately this V in get divided across this R1 and R2. So let's give a polarity first of all to them. So a point where current enters will have a positive polarity, and where leaves negative polarity. In the similar way, here you should denote positive polarity at incoming terminal and the negative polarity at outgoing terminal. The reason behind is this notation is like the current will flow only in this direction when a potential which is available at this node is higher than the other node. Then and then current can flow from one end to another end. In the similar way, it is the same argument is valid for the second part, right? The current should will only flow when the potential available at this end is higher than the another one. Now, so the overall current can be found like V in upon R1 plus R2. Now what will be the potential drop across this R1? So R1 is I into VR1 is I into R1, right? And in the similar way you can write here I into R2. Now we are interested in, let's say, how much V1 will be there and how much V2 will be there, right? The potential drop which take place across R1 and the potential drop which is take place across R2. Now here we can write the final formula V1 equal to I into R1. Now what is I? So from this equation you can substitute the value of I, and so here you can write V in upon R1 plus R2, and R1 will be there. Now take V in out and put this R1 in. So in the overall sense you can write here R1 divided by R1 plus R2 into V in. Okay. So see, if you want to find the voltage drop or the potential which divided across this R1, so this is nothing but the its own resistance divided by the total resistance into input voltage. In the similar way, if you want to find the voltage which is voltage drop across R2, so this will be R2 its own resistor divided by the whole resistors, means R1 plus R2 into V in. So you can also write for V2. So V2 can be given by I into R2. So in the similar way we can substitute the value of V in upon R1 plus R2 into R1 into R2. Yes, so here this will be its own resistor divided by R1 plus R2 into V in. Okay, so this is all about voltage division rule. Now let's move to current division rule. So in current division rule, the two or more than two resistors are connected in parallel. So let's discuss this case with a two resistor are connected in parallel. So let's say if we have two resistor R1 and R2 as given here in the figure, and both the resistors are connected in parallel. So keep one thing in the mind, that the resistor are only said to be connected in parallel if voltage which appears across these two resistors having the same value. This is what we have discussed in the parallel combination of resistor. Now here we are interested in the current which divided into this R1 resistor So I1 and this I2, and overall current is I. Now see, the voltage V in is appear across this R1 as well as appears across R2, because ultimately they are connected in parallel. So from that you can write Ohm's law like V1 or V in equal to, so here if you write at this and this node, V in can be given by I1 R1. At this and this node you can write V2 V in equal to I2 R2, right? So both are the same value, right, because V in and V in. So you can compare both the value, so you can write like I1 R1 will be I2 R2. Now if you apply KCL over here, so you can write I equal to I1 plus I2. Now let's say if you make I2 as a subject, so from this equation you can write I2 equal to I1 R1 divided by R2. So you need to substitute this value in this expression. So here you can write like I1 plus, so you need to replace I2 with I1 R1 divided by R2. So make I1 as a common, so ultimately you will have 1 plus R1 divided by R2. This will be overall current I. Now you simplify this term, so you can write I equal to I1 into R1 plus R2 divided by R2. And when you make subject I1, so I1 can be given by R2 divided by R1 plus R2 into whole current I. So see, when you observe the figure, so I1 is nothing but the resistor which is connected in parallel with that particular resistor, means R2, divided by the whole resistors, means R1 plus R2 multiply with the overall current. So if you want to find the current at I2, so you can write like the resistor which is in parallel with the R2. So this is R1 divided by R1 plus R2 into I current. So for the I2 you can write that it is ratio of R1 divided by R1 plus R2 into the net current, which is I. So this is how you can derive the current which is get divided into parallel combination of resistor. So that's it. So we have discussed all the parts like series connect combination of resistance, parallel combinations of resistance, current division and voltage division rule. So please like, share and subscribe this channel. Thank you.